Good morning, everyone. So today we record the MATH102 Recitation Lab for week 9. And this is the outline of the presentation. We start by solving the exercise at the end of week 8. Then we'll move on to arc lengths and surface of revolution, which corresponds to section 7.4 from our Calculus book. So we'll have 2 examples and 1 exercise for next week. So let's start by the exercise at the end of week 8. Here it's said week 7, but it's at the end of week 8 because we have a different configuration for this semester 232. So the exercise said use the method of cylindrical shells to find the volume generated by rotating the region bounded by the curves y equals to e to the power minus x squared, y equals 0, x equals 0, and x equals 1 about the y-axis. So we'll start first of all by uploading the file of week 9, and which is week 9, exercise 8, week 8 integration. And this is a wrong abbreviation, of course. This is our file here for the arc lengths and surface of revolution. So we'll import the packages and the functions needed as usual. And here for this problem, we start first of all by defining the x and y variables using symbols from SymPy. And of course, x and y here need to be real numbers. We'll plot the graph of f of x, and then we plot the line x equals 1 and plot the graph with this line. So this is here what you see in this slide number 4. This is the plot of e to the power minus x squared, and here is the line x equals 1. For the Python file, here it is. So here, notice that we imported everything from SymPy to avoid any problem. P1 is the plot of the function e to the power minus x squared, and P2 is the plot of x equals 1. Okay, and we extended the 2 plots over each other. So here it is. Okay, so in the next slide, we are ready to plot the region to be rotated, which is bounded by the by the y-axis, x equals 1, and the our graph. So to do this, we use P3, which is the implicit plot, which takes into account these conditions: x less than 1, x greater than 0, y greater than 0, and y less than e to the power minus x squared. And intentionally, we try to make x between -1 and 1, y between -1 and 1, and we'll get this shaded region. Here is our Python file, Jupyter Notebook file, to be more precise, and here is P3. So basically, we want to rotate this with respect to the y-axis as they asked it in the question. So to do this, we are ready to integrate using what we call cylindrical shells. So we remember from the cylindrical shells, we need the radius and the height. So the height here for our cylindrical shells would be given by the function itself, e to the power minus x squared, and while the radius is x. And remember, the formula for the integration here for the volume would be 2 pi the integral on the boundary on x of r times h, integral of r times h. And the integration is with respect to x here, even though we are rotating with respect to the vertical axis, which is the y-axis, because we are using the cylindrical shells methods. Okay? So we'll first integrate, and we will also use the command simplify, which is a new command to add to your tools. Simplify to get a simpler expression. So this is what we get from our Python file, exactly what we have in the slides here in cell 6. And we have the integration of 2 pi rh between 0 and 1. And here's the simplification. So the final result is pi minus pi over e. Okay, so here we close section 7.2, 7.3, and we move on to section 7.4. So we start talking about what we call arc lengths. And here we would like to find an example 1 to sketch the graph of this following equation or following curve given by x to the power 2 over 3 plus y to the power 2 over 3 equals 1. And we would like to use symmetry to find its length. So first of all, as you see here, we import everything from SymPy. We define our xy as symbols, variables, and we plot the implicit curve here, given by x to the power 2 over 3 plus y to the power 2 over 3 minus 1. And we'll make sure that we are using a convenient, let's say, scale for our graphic. So here, for instance, x between -2 and 2. So this is the plot of the implicit curve, and here we are in the Python file. Got it? So we'll now move on to the next slide. So it's clear from the last plot above that we can use only one quadrant and multiply by 4. That's why we are using symmetry with respect to the x-axis and y-axis. And on the first quadrant, one could say that y is positive, so y is equal to 1 minus x to the power 2 over 3, all to the power 3 over 3. And x is between 0 and 1. So we'll just take this part here. Okay? So we'll avoid here using the integrate command directly, because it would take a long time. And instead, we will use a step-by-step approach, which consists of getting each piece of the integral alone. So the first step would be to write y as 1 minus x to the power 2 over 3 to the power 3 over 2. And we write the integrand, okay, which is 1 minus x to the power 2 over 3. Here it is. First of all, this is what we did. Okay, so this is y equals 1 minus x to the power 2 over 3, all to the power 3 over 2. Okay, we wrote it in simpler form using this rational command from SymPy. Then we will define z as 1 plus the derivative of y with respect to x, of course. Since in the formula, we know we'll have to integrate the square root of 1 plus dy over dx squared. So z would be 1 plus dy derivative of y squared. Okay, that's it. We got this. This is the display of z. Here we go. Simplify. And then we take the square root of z and we substitute 1.0, because here we have 1.0. We'll just modify it. We'll just substitute it by 1 and make it more simple. So we get a simpler form for z, which is 1 over cubic root of x. And here we go. We are ready to integrate. So the volume we get would be 4 times the solution by the integrate command. The integrate command will give us a very simple thing here. So the volume would be 4 times integrate of square root of z when you substitute 1.0 by 1, when x between 0 and 1, and you get a volume of 6. Okay? So remember, the main steps here were to decompose the integrand into pieces using the rational command. Otherwise, it would take too long time to integrate. In the example 2, we have to find the arc length function for the curve y equals 2 times x to the power 3 over 2, with initial point, which is p0 or p0, 1, 2. And we may use the arc length function obtained in 1 above to find the length of the curve when x is between 1 and 2, 1 and 3, or 2 over 3. First of all, of course, we import the necessary libraries. We declare the symbols x and t, and define y given in the question as a function of f, and we compute the arc length. So here is the definition of x and t as the variables here, and we define y to be 2 times t times the rational to the power rational 3 over 2, rational over 2, which means this is 2t to the power 3 over 2. Then we define s to be the result of the integration of the square root of 1 plus the derivative of y squared. So that's basically the arc length formula we're going to have in terms of x when t goes from 1 to x. So this is the arc length formula, s, we got in terms of x. All we have to do now to get the result is to substitute for every corresponding value of x or upper bound on x. Here, for instance, we substituted. We use the command subs to evaluate s at the value of x equals 2. And this is what you got. And for the eval f, give us the exact numerical value. So we insist on the fact that if you may have a solution in these two forms, either in this root form or in this numerical form. Okay, so if you want to get the exact value, just use the eval f, and it's better. Okay, so we can do the same for b when x equals 3. So the upper limit is 3. We get 8.6325, or for the difference, which is when x is between 2 and 3. So we just remove the part which goes from 1 to. So we just here do the difference between what we got in B and A. So this is the arc length from 2 to 3. Okay, so here it is. So we have an exercise for next week, and we'll talk about the rotation about this curve y equals square root of 1 plus ex, when x between 0 and 1, about the x-axis, and we would like to find the area of surface of revolution here. So the next week we talk about the area of surface of revolution. So here it is for this presentation. Thank you very much for following us, and good luck for the next.